Hi, everyone. Welcome to our session, The Path to LLM Adoption, Key Use Cases, Benchmarks, and Trust Building Strategies. I'm Alex Januszewski, Senior Director of AI Solutions.
And I'm Jason Raukwerk, MT Deployment Engineer. So I will be discussing some improvements in our AI toolkit, including updates on our fuzzy match repair, glossary term insertion, smoothing, and what we call edit effort estimation. And then I'll discuss a little bit on how we can best utilize AI post-processing. So first, I'd like to discuss the performance of our recent updates to fuzzy match repair in Q1 of this year. Some of the updates to the prompt include more robust retrieval augmented generation, translation memory examples, and explicit glossary entries. We are using state-of-the-art LLMs, including Gemini Flash 2.0 for this task. We've also added a threshold to avoid damaging good, this is about 95% match strings. And while we've made great improvements to fuzzy match repair, mistakes can still happen. This is generally a result of hallucinations or possibly bad translation memory data. This happens most often with numeric values, including dates or times. And we have managed to mitigate most of these issues, which I will discuss later in this presentation. Overall, these improvements have given an average of 25% to fuzzy matches using these new updates. So this means that something that would originally be considered a 60% string match has now become about an 85% fuzzy match. This is a great improvement, and it also means that these new matches have a lower cost incurred. And now I'll talk about some of our other AI toolkit features. So formality handling has been migrated to Gemini 1.5 v2 Flash, which immediately, without even having to change the prompt, has provided significant improvements. One challenge that we've made significant progress on is when the model becomes too informal, using very casual or sometimes even pejorative language, but we've managed to mitigate this as much as we can. Glossary term insertion is also currently working at 80 to 90% accuracy, depending on the language, and moving to Gemini Flash 2 will boost that performance even more. And we continue to iterate on that prompt as well. String smoothing has also improved recently. Our current LLM for this task is GPT-4o, although we are currently testing other models to benchmark their performance. Finally, linguistic quality estimation, which we call edit effort estimation, or EEE, can be enhanced by the use of custom-trained models. With a trained engine, our accuracy has improved up to 60%. In a three-label prediction problem like this, the random baseline is all the way down at 33%, so this is a 100% improvement over that baseline. However, accuracy doesn't always tell the full story. The second graph shows the precision metric on strings labeled as no error. Precision states which proportion of strings labeled as no error really fit the category. Generic models struggle with this task, but our custom-trained models have an average of 83% precision. This is important because no error strings may be skipped for automated post-editing. I'll discuss more about that later in this presentation. Finally, I would like to discuss how customers can ensure they get the best results from our AI toolkit. We generally can divide performance in AI tasks into three categories. First is when the client doesn't have any linguistic assets. We can attempt to use AI toolkit features, but our main use for AI is to make sure that translations are personalized to the customer's brand. Without linguistic assets, this is largely a futile effort. Next, when the customer has somewhat consistent linguistic assets, they can gain some small amount of leverage from the translation memory, and the customer uses a generic machine translation engine like our AutoSelect. In this case, they can reap some of the benefits of AI Toolkit, although their performance will not be as good as the third type of customer. When the customer has clean, consistent, and reliable linguistic assets, they will also have very good leverage from their translation memory and have the ability to train custom machine translation engines to start with good translated text. This effect will compound with AI Toolkit and provide the best results. The takeaway from this is that to achieve the best results with AI, we need to start with the best and cleanest data.
I'm going to do a deep dive and talk about new and updated use cases. So LLMs, large language models, are becoming quite popular. So this naturally begs the question, when do we use the current technology, neural machine translation, NMT, versus large language models? And I think we're getting to an inflection point, and the scale is tipping in favor of large language models. However, we wanted to give an idea of when each one can be used because each technology has its own strength and weaknesses. So, in the case of neural machine translation models, so the current technology, so think, for example, Google Translate, DeepL, Amazon, etc., we find that the translation tends to be more literal, but there tends to be better adherence to brand terminology. And this content is generally suited when there's a human in the loop and the content itself is less creative. On the other hand, large language models tend to be more fluent and natural sounding. However, this comes at the expense of less adherence to brand terminology. This could be a scenario where you might want to use large language models for content that is a bit more creative and perhaps when there's no human in the loop. So the question then ultimately is when to switch, right? When do we get to that tipping point? We would say right now, use both potentially based on the content that you have. So if you have less creative content and a human in the loop, perhaps neural machine translation. Whereas if it's more creative content, needs to sound more snazzy, then perhaps a large language model and there is no human in the loop. So let's talk about other use cases for large language models. So for us, when we're looking at large language models, ostensibly they could be used everywhere in the globalization workflow, starting from source editing, where you could take source, for example, and make that source edit it and make it available for higher quality translation. So think about something like UGC, user generated content, right? And you might make that a bit more understandable so it's much easier to process for a machine or human being. In the last slide, we were talking about this case, which is can we use large language models as an empty provider? So instead of using neural machine translation, just use this direct AI technology. Lastly, and I'm skipping over this for the moment, is the idea of localized content creation, or what we would call death to the source. So rather than authoring, let's say in English and translating into Spanish or translating into Arabic, Chinese, etc., what if we made a prompt to a large language model, a very targeted prompt that said, I need to write a blog post of 300 words based on this topic. Please write it for me, right? In this case, we don't even need the source because we're going to start out with the target language as it is. Now, in our case, we're going to focus on this, which is translation augmentation. So the idea here is we have our machine translation from this step. And now we're going to augment or post-process this using a bunch of different microservices in order to improve the translation before it goes to the linguist. What we found is when we do this automated post-editing, it increases the quality very dramatically by 4 or 5 MQM points. So MQM stands for multi-quality dimensional framework. It's the best practice. It's the standard that's used to gauge translations for major, minor, critical, and no errors in the industry. So an improvement of 4 or 5 points by using large language models to augment the automated translation is a very, very significant jump. And this is where we're putting the vast majority of our efforts. So let's talk about benchmarking large language models, right? So clearly, large language models are here to stay, but how do we know that they're good? And I want to separate here two different facets of benchmarking. One is evaluation and the other one is estimation. So how do they differ? Evaluation presumes that you have a reference, you know what's good, and you're striving towards that goal. So in this case, we have our source in English, we have our reference or good human validated translation in Spanish, and we have our automated translation. And what we're trying to figure out is how well does this translation equal to the reference, right? How little do I have to edit to get from here to here, and how closely do they match? When I'm doing the task of estimation, I don't have a reference. I don't know what's good. So what I'm doing is I'm trying to see how well does this machine translation represent the source? Is it a good translation, right? And I have no anchor. I have no reference. So they're slightly different tasks, but they use some of the same technology. So one way to do benchmarking is textual auto scoring. So what we mean here, and probably some of you are familiar with concepts like blue score or translation error rate or translation edit distance rate. So the idea here is I have my source string, I have my validated reference translation done by a human being, and in this case, I have my trained machine translation. So the question here is if I'm a linguist, how much do I need to edit this sentence to get to this point? And you'll see we marked in bold the differences. In essence, taking these two words, moving them to the beginning of the sentence to reorder them, and then the last sentence is by and large exactly the same, which is pretty impressive for a lengthier sentence. And we see this reflected in the character edit distance, which is a mere 6%. So think of this as a very, very high fuzzy match that would be paid accordingly because for me as a linguist, there isn't that much to edit. So that's one of the measures that we use, and it's called textual auto scoring. Now, this is all fine and good, but there's a problem where this fails. There are some corner cases. So think of situations where the words are exactly the same, but the punctuation is slightly different. So let's eat, comma, grandmother would be, hey, grandmother, come to the table, let's eat, right? If we take out this exclamation mark and this question mark, this has a completely different meaning, which I'm not going to go into, but you can imagine. And it's not particularly good, right? We see a similar idea where textual scoring fails when the words are very small. So the difference between the defendant being guilty versus not guilty is only 3 characters, 1 word, but that word completely flips the meaning. The same way here, whether we're going to pour gas into our car or oil into our car, at this point, it's 1 word, and these 3 characters may completely cause me to ruin my car. At the same point, we can see that the edit distance here is very, very low, right? So how do we account for these cases? And this is where semantic scoring comes in. So the idea of semantic scoring is representing words as numbers, right? So this is the idea called word embeddings. So we as human beings deal very well with words. Computers don't. It's much easier for them to calculate numbers. So what we can do is we can put numbers to represent words with all of their different contexts. And the notion is that words that are similar to each other are plotted next to each other, adjacent to each other in a 2 or 3D space. We can't go more than that because for us as human beings, we can abstractly conceive of something having 1,000 parameters, but we really can't see that plotted, hence a 2 or 3D space. So what you're seeing here are words or concepts that are closely related to each other. So for example, walked and walking, swam and swimming are closely related to each other, right? Male and female, so king and man, woman and queen. We can do the same thing with capitals. Madrid is the capital of Spain, so they lie close to each other in a 2D space. Certainly, Beijing is not the capital of Spain. That's why they're further apart. Again, we see this with other words where jump and bounce are related. Walk, run, and jog are related, but they're not related to each other. And blink, you can see, is related to none of these, right? So this is fine and good. It's awesome that it works with words, but we can take this further and we can expand this into sentence embeddings. So here we look at the entire sentence, and sentences that are related to each other lie in the same space. So we can see that these 2 sentences, right? We've got a lion and a tiger, we've got a jungle and the forest. They're related to each other far more than this sentence, which is completely different. Now, we could also further stack this and essentially, when we have translations that are a good representation of the source will be in the same space. And we see that here. Here's our English, German, and Japanese. They all lie in the same space. This is a different English sentence, and you can see that it has very, very, very little relation to the others, right? So how do we actually use this pragmatically in real life? One of the ways is, and Jason will mention it a bit later, is this is one of the methodologies that we use for determining whether the LLM has hallucinated or not. But another way that we can do this is if we have a lower score, it may indicate that the sentences don't match. So here's a sentence where it's a good translation in French, except for Alyssa has become Florence, but we can see scores ranging from 70 to 86. When I change the sentence in yellow and it makes no sense, we're even beginning to see negative numbers, right? So this is a very, very good way for us to tell whether we're giving erroneous information to the user and whether this information may not adhere to the brand tone or the style. So we talked about this inflection point. What we're seeing thus far is trained neural machine translation. In this case, we're showing Google AutoML is still outperforming both on textual scoring and semantic scoring over large language models. So you can see, for example, here, a higher blue, a lower edit distance, a higher meteor score, and a higher comet score. And particularly, this is a score that we use for semantic scoring, metric X by Google, where lower is better. So pretty much across the board, you see that the trained neural machine translation wins. And this is just a snippet of a couple of languages that tell a similar story. But and this kind of goes back to what we were saying earlier. This is great for a production human in the loop scenario, but we're seeing large language models advance, and we expect that probably in the next year, if not sooner, perhaps even 6 or 9 months, these large language models will begin to catch up and overtake neural machine translation models. So one other thing I wanted to talk about is opportunities for inclusivity and DEI. So this is actually a very relevant case that is coming from one of our clients where the governor of New York became the first female governor, Kathy Hochul, right, who replaced Governor Cuomo. So the issue that we faced here is that we were doing machine translation. And for example, English doesn't demarcate gender unlike other languages. So in Spanish, for example, unfortunately, because the generic models are so biased towards the male point of view, we would translate governor, which has no marking in English of gender, into Spanish, and it would say el gobernador, which is male, right? And the trick was to change all of that into female so it would be far more relevant, and of course celebrate that now we have a first female governor of New York. So how do we do that, right? So here's our text. If we were doing this the traditional way without a large language model, we would get the male version. Right? With a targeted large language model prompt, we're actually going to get a version that gives us the feminine version, La Gobernadora, right? And the other part that's very nice about this is we can also have anything else in the sentence that relates to the feminine gender, for example, be it a verb, be it an article, be it an adjective, would also now match the female article and female noun. So another experiment that we did to kind of take this a little bit further is to see if we could get large language models to convert pronouns from masculine to feminine and from masculine to non-binary. Again, this goes to the idea that in a lot of models, traditionally, you would have masculine roles take on a masculine noun. So we wanted to undo that. So we did this 2 different ways. One is we would take the source, which was masculine, we would translate it, we would get a masculine translation, and then we would write a prompt to the large language model and convert this into either non-binary or feminine. That was one way of doing it. The other method of doing it is we would say, okay, we're going to take a masculine source, we're going to have a large language model step in here and make it feminine or non-binary, and then having this already as the source, non-binary and feminine, we would commence and do a non-binary or feminine translations. And we did this in several different large language models, both for feminine and non-binary. And what you'll see is when we did the conversion into feminine, by and large, no matter what method it was, we were hitting 80% with a full-fledged proper conversion. And the difference between these 2 numbers represents partial success, meaning that we got the pronoun correct, but perhaps other things in the sentence were not correct. But the important thing is that we were at 80% or higher with all of the large language models. Unfortunately, you'll see that when we were dealing with non-binary, these numbers tended to be a lot lower, and even the best performing of the large language models only hit 57%. So this is an example. This is a snippet of a prompt to convert from male to non-binary. So you could see here two things going on. Number one is the specific instructions to the LLM of what we would like it to do with the Spanish text. And equally as important is an example to the large language model of what we consider to be a correct transformation. So the notion here is that the large language model should learn from this example and then apply these instructions. Right. So again, to sum up these pronoun conversion experiments, we see a conversion from masculine to feminine. We're seeing an 80%, over 80% success for all models, and it's ready for production. When we're dealing with non-binary conversion, the best performing large language model is only at 57% accuracy. So clearly it's not ready for production use at the moment. However, where we see a future progression for this is we believe that large language models will continue to get better, and we expect that we're going to see a progression and a much better way to deal with non-binary forms and include them in the language transformation. So other experiments that we're working on is changing the terminology to be more appropriate. So now I'm going to go back to Jason, and he's going to talk a little bit about building trust in large language models and reducing hallucinations.
So now let's pivot to talk about the reliability of LLMs or large language models. An analogy that we like to use is that LLMs are a precocious youngster. They are very intelligent, but they lack the wisdom and the common sense to apply a lot of this knowledge in the most correct way. Here's a real example that we encountered just last month. So I don't speak German, so I can't speak for the accuracy of the translations at the top and bottom, but even I can tell that there isn't a numbered list in that middle string, so something here went very wrong. So what's going on? We can see that the model did ultimately translate to German, but it also took the request seriously and tried to answer this prompt that the user entered. This is very far cut off. The original response contained 4 or 5 bullet points, each with 4 or 5 sub-bullet points. So something just very crazy happened here. So when even the top of the line AI models can fail so catastrophically, what can we do about it? And how much autonomy are we willing to give these models? We can curate our prompts to prevent hallucinations as much as we can, but sometimes even these precautions can fail. So we have to rely on our ability to detect hallucinations and prevent them from reaching the final translated strings. Some relatively simple ways of detecting them are to use the source to target length ratio, semantic similarity metrics, or, as I kind of said before, utilize the prompt to specify a default response that the model can fall back on, like saying, I don't know. So the source to target length ratio is exactly what it sounds like. You take the ratio of the words or characters in the source and in the translation. If that ratio is too high, we know that something probably went wrong. This is not foolproof. Different languages can naturally have different ratios. So, for example, closely related languages that share an alphabet, like English and German, this can work very well. This is how I was personally able to determine that something went wrong in the example that we just showed. However, these ratios may be skewed in some languages. Like when we're comparing English to Chinese or Japanese, there just really isn't a one-to-one correlation between words here that we can easily use. So for cases like these, we can use semantic similarity metrics to help. Alex has mentioned this earlier in the presentation. Essentially, if these dense vector representations of these sentences are close together, we can be reasonably sure that the translation is fairly accurate, or at the very least, not a hallucination. And within the prompt, we can tell the LLM, please, specify if you don't understand the request, if something is wrong. Uh, this doesn't always work, but it can be fairly effective. Now, I'd like to introduce a more complex approach. So this is called log probability. Essentially, a large language model is modeling language, and each word has a certain probability associated with it. At each step, the model decides which word it's going to translate next, based on some probability distribution. We convert these probabilities into the logarithm. We take the negative logarithm of this to make these very small numbers into something palatable for humans. And what we can do is we can look at the the probabilities for each individual word. We can look for peaks or valleys, we can look for the variance between the different probabilities, and we can see how it correlates to edit rate. What we can see is that lower probability generally results in a higher edit rate. This makes sense. A more obvious word will have a more high probability and will be more likely to be chosen. But when we get smaller, unpredictable things can happen. So what else do we do? This is a quick example of post-processing underneath the hood. The main takeaway from this fairly complex flowchart is that for each step that utilizes a large language model, smoothing, glossary term insertion, formality, there is always a validation step. We always make sure that we have some number of checks to make sure that we are not letting random hallucinations through our automated post-editing steps. Another example is for edit effort estimation. This model is very, very good, but sometimes mistakes can be made. So we use both edit estimation and our own custom quality checks to ensure that we can skip the correct strings. We don't want to skip strings that need editing. This is very important to us. So we make sure we always have a double check to make sure that that never happens.
I'm going to conclude by talking a little bit about our R&D roadmap. So this is a recap of the features that we released in 2024. We released adaptive translation memory, fuzzy match repair. That's what Jason was talking about, and further improvements that we made to it. Glossary term insertion, a more grammatically correct way to insert glossaries using large language models. We also introduced informality for Spanish, German, and Italian, the ability of using large language models to evaluate the translation, and again, as Jason showed, fine-tuning models for edit effort estimation for even more accurate translation evaluation. And we introduced the ability to translate directly using GPT models. So what's in research and in MVP right now that's going to be getting into the platform in the very, very near term? Things like LLM translation smoothing. So this is already in the platform and we're further iterating on this. Um, Also, as we see this inflection point and using basically built for purpose translation large language models, right? Google Pet LLM is an example, and that's going to be integrated into the platform very, very shortly. We're also moving philosophically in the direction of we want to give the best automated translation, be it using adaptive translation memory or be it using LLMs as an MT provider or specific LLMs. We ultimately want to arrive at the best automated translation with a combination of automated translation plus various smoothing mechanisms. We're also working very hard on introducing a reliable, high-performing auto MQM as an auto LQA measure. This is extremely important so we can give clients the ability to do targeted LQA, right? When you're done with all of your steps in the human translation, how can we tell the LQA person, rather than randomly choosing 10% of the particular file or of all of your project, right, all of your job, how can we say no? Focus on these because these have the greater chance of having issues. And that's where doing high performance, highly reliable auto MQM becomes very, very important. And this is coming a little bit later, longer time frame. So things like expanding large language model support for large language models, self-hosted large language models. We're also working quite a bit on source content pre-editing. In other words, let's not assume that the source is always good and correct. Can we flag complicated source because we know that that might lead to a cognitive load either for machines or for translators down the line? And finally, we're working on introducing prompt engineering tools. So we actually have quite a bit of prompts that we're using with client assets, but what if clients want to come in and customize their prompts? How do we give them the wherewithal to do that? So we hope that you'll see all of these things in the platform in the near future. And thank you very much for joining our session.